Thank you everyone for being here. Actually, I'm very excited to be back at SciPy. The last time was 2017, and I gave a lightning talk back then. Now it's a different type of lightning, a slightly longer talk. Many academic conferences in between 2017 and now, but I always tell people this is really where all the fun is. I'm not lying, it's my favorite conference because the open source community, all the tinkerers here, and so many familiar and new people I met here. It's a pleasure to be here, and thank you everyone for coming. So today I'm going to talk about using deep learning when class labels have a natural order. And why is that interesting? That's because many real-world applications have ordered labels, as we will see shortly. So also, I have all the code material and slides here on GitHub. So there will be a short code example, lots of slides, but no need to, let's say, take pictures. It will be all on GitHub. I think, unless I forgot, it should already be public, unless I forgot to make it public because I set it to private first. Okay, so getting started then. So why do we care about ordered labels? Like I just mentioned, there are many real-world problems where we have ordered information. For example, Amazon ratings, where we have 1, 2, 3, 4, 5 stars. Let's say damage assessment. Insurance companies use like some rating scale to assess the damage of buildings, for example, or maybe the most popular of all, the famous Likert scale for estimating or collecting customer satisfaction ratings. So to dive a little bit more into this ordered label problem, I wanted to give you a few examples also why that matters. So how, in particular, how do these ordered labels differ from, let's say, regular class labels that we usually work with when we, let's say, apply off-the-shelf machine learning algorithms, let's say, from scikit-learn or deep learning architectures. So in regular classification, you probably already stumbled maybe many times over the iris data set, where we have different flower species. So in iris, we have these 3 flower classes or species, iris setosa, versicolor, and virginica. And there is no ordering information among these classes. So they are just like disjoint, independent classes. And often when we then, let's say, translate that into a data array, we assign numeric labels, like integer labels, like 0, 1, and 2, or 1, 2, and 3. And so it kind of like looks like, okay, there's, 1, 2, 3, it's like order here. But in fact, they are totally unrelated categories. So I can't really say, let's say, setosa is less than versicolor, or versicolor is less than virginica. So there's no ordering relationship between these labels. They are really independent. However, if I have a slightly different problem here, like these ice cream scoops, here I have 1, 2, and 3 ice cream scoops, I can really say 1 ice cream scoop is less than 2 ice cream scoops, and 2 ice cream scoops is or are less than 3 ice cream scoops. So here, it's more like a regression setting where I have numbers that actually have an order where I can make comparisons here. And even more, so if the ice cream scooping person did a good job, so there should be identical distances. So the difference between 1 and 2 ice cream scoops should be the same as 2 and 3 ice cream scoops. So I have like these numbers that I can directly compare, right? So, or if I have a 1.5 ice cream scoops, so I have half difference between 1.5 and 2 and so forth. So I can really play around with these numbers, and these numbers kind of like make sense. I can quantify things here. However, there are also these different types of labels that have an order, yet they are a little bit more, I would say, arbitrary. So here I just picked 3 movies I watched in the past. I hope I don't offend anyone. So these smiley faces indicate how much I like each of these movies. So I have, let's say, an unhappy face regarding Transformers, the movie, not the architecture, and neutral face for Star Trek. Sorry, everyone, and a smiley face for the old Star Wars movies, at least. So here I have now some information. I have some ordering information here, and then I can also translate that to numbers. I can say 1, 2, and 3 in terms of how well I like this movie. And furthermore, I can then also have an ordering. I can say 1 is less than 2, and 2 is less than 3. However, in contrast to, let's say, this regression problem, I can't really quantify, let's say, how much more I like Star Wars compared to Star Trek, and then comparing this distance to, let's say, Transformers and Star Trek. So these distances are somewhat arbitrary. I would have a hard time, like, putting like precise numbers on those. So here, it's really like the difference between having ordering information, but yet not knowing the exact, let's say, quantities here. So, and in the remainder of the talk, I will tell you how we can deal with such problems. So, but naturally, you might wonder, okay, can we just use a regular classifier for such problems? I mean, it's still, there are still kind of like categories, so we could actually use a regular classifier, let's say support vector machine or multilayer perceptron with a softmax and cross entropy loss and so forth. Yeah, we can do that, and actually many people do that, and it doesn't, it works, but it's not ideal. So it is possible, but there are better ways for like these types of problems. And the reason why, if we apply a regular classifier to these ordered labels, why it's not ideal, is because all the, let's say, wrong predictions will look equally wrong to the classifier. So to illustrate this with a problem here, or with an example, let's say we have a correct prediction where I have this unhappy phase. And so this would, this would be the correct label. And there are now two types of predictions I can make. So I could either predict this unhappy phase, that's the neutral phase. So I can either predict the neutral phase, which is wrong if unhappy is the correct one, or I can predict the happy phase, which is yet another wrong prediction. However, so for a classifier, both would be equally wrong. However, if we think about it, this smiley face, the green one on the right, would be more wrong than the neutral one because it's farther away from the unhappy phase. So I have additional information about how wrong my prediction is. And incorporating this information during, let's say, the training of a neural network or machine learning classifier will convey additional information, like helping the classifier or the model learn to make better predictions, so being less wrong, let's say. So because, yeah, this one on the right side, like I mentioned, should be more wrong than the neutral phase. And yeah, again, why do we care? Like I mentioned before, there are many real-world problems where we actually have ordered information. So you may or may have not worked with a data set where you have ordered information, but I think it's always a good exercise to think about it. If you have a given data set, does it make sense, let's say, to compare class labels, to kind of like think about whether an ordinal regression model would make sense. And I will show you it's actually very simple to use any, let's say, any neural network, make a few changes and turn this into an ordinal regression network. So we can, in fact, then get much better performance by using an ordinal regression approach rather than, let's say, using a regular classifier. So there are different methods for doing that. And so here in this talk, I will show you one way of doing this, using something most of you, or we already used in many other problems. And this will be based on binary classification. So I will show you an extended binary classification framework for turning a classifier into an ordinal regression model. So to give you an example of how that would look like, so here I have an input image. It's from an aesthetics data set where someone assigned, let's say, ratings from 1 to 5, how, let's say, aesthetically pleasing an image is. Just as an example, so we can have the possible rating labels 1 to 5. And then we would put this through a network. So this could be any network. So everything I'm talking about here, it could be any type of network. It's a very general approach. So here it could be a convolutional neural network, a recurrent neural network, a multilayer perceptron, a transformer, and so forth. In this case, I would probably use a convolutional network or a vision transformer because it's an image. But in general, you can use any type of network here. And then the output nodes, you can think of them as, let's say, sigmoid activations that return a score. So the score would be between 0 and 1 for each output node. And you can think of these output nodes as like probabilities whether the label exceeds a certain rank. So the first output node would be whether the true label of this image is greater than 1. The second node, whether it's greater than 2. The third node, whether it's greater than 3, and so forth. And so what do these scores mean? So you can really think of them as a binary classification task. So you can basically think of the first one, is the rating greater than 1? Yes or no? So it's in a sense turning this problem, this classification problem, into multiple binary classifications. So you have then at these output nodes these binary questions. So you have here in this case, if we have 5 labels, we have 4 output nodes. Because when we answer the last output node with yes, so if we answer it's greater than 4, this would imply 5. So we have one fewer output node than we have ratings. But yeah, so this is the basic idea between or behind turning a classifier into this ordinal regression model using extended binary classification. So how do we now then obtain the rating label, the predicted rating? So we would essentially sum up the yeses on the right-hand side, so the number of yeses, by applying, let's say, a threshold to these scores. So we can say if the probability exceeds 50%, we say it's a yes. Otherwise, we say a no, and then we sum up the yeses, add a 1, and get this rating label. So here's an example for this particular image. For example, let's say for the first node, we have a score that is greater than 50%, so it's a yes. Then for the second one, we also have a probability that is greater than 50%. It's another yes. And then for the other ones, there are no's. So when I sum up the yeses, add a 1 to it, I get essentially the predicted label of 3. So in that case, that's how I turn the scores into these binary responses and then into a predicted label. And yeah, this works incredibly well. So this is something that has been used. I think I skipped the paper. There was a link to the paper on the lower left hand side. This was a CVPR 2016 paper by New and colleagues. And this works incredibly well in practice. However, there is one little issue with that, and that is rank inconsistency. So what can happen in practice if you use this approach with a neural network is that you get like these little paradoxical statements like rank inconsistencies, which here means, for example, you may predict that the rank is greater than 4, but it's not greater than 3, and that doesn't really make sense. It's like a paradoxical statement. You may still get the correct label prediction, but still it's not quite right. And we basically addressed this rank inconsistency issue and found that this can then also improve the performance of this approach. So one way of addressing this rank inconsistency problem, we called it Coral, is something we worked on about 2 years ago. And by having a little constraint on the output layer. And so applying this approach, we found that, we can fix this rank inconsistency issue. At the top, I'm showing you the reference network without this, let's say, correction. And on the bottom here, that's our Coral approach where we have this little rank inconsistency. I won't go too much into detail of how this Coral method works because it's a relatively short talk, and it also has a limitation I wanted to briefly mention. And this Coral method, in order to have this guaranteed rank consistency, we had a theorem that required us to share or to have shared weights in the output layer. So we are kind of like constraining the network in terms of what it can do. So again, without going into too much detail, there was a weight sharing constraint in the output layer, and as a consequence, the output nodes only differed in their bias units. I mean, this worked incredibly well. It worked better than the rank inconsistent method, but it was still not ideal. So recently we developed a new method where we, let's say, removed this weight sharing constraint. We called it CORN, because it's based on, I'm always bad coming up with acronyms, but it's essentially in a nutshell, it's based on the chain rule for probabilities. Also, again, because, I mean, it's a short talk, I don't want to go into too many mathematical details, because I really want to get to the brief code examples. So, but in a nutshell, how this works is at each output node, we compute a conditional probability. For example, here, I'm highlighting the output node 2, and at this node, we are computing the predicted probability, conditional probability, that the label is greater than rank 2, given that the rating is greater than 1 from the first node. So it's essentially this conditional probability that we can then learn with a so-called conditional training sets. And how these conditional training sets work, that's detailed in the paper. But so the main idea is essentially applying the chain rule for probabilities, which is also in statistics called the general product rule. So it's essentially just multiplying these conditional probabilities to obtain the unconditional probability. And just to have one quick example here at the bottom for this output node I'm highlighting. So for example, to compute the probability that this output node 2 exceeds rank 2, we would have the conditional probability of the second node times the probability of the first node. So for the first node, we don't have a conditional probability because there is no previous node, but all the other nodes are essentially conditional probabilities that we can compute with these training subsets. And I mean, long story short, I mean, if that doesn't make sense, it's a very brief outline here. Don't worry about it. So the main message is because we have probabilities between 0 and 1, if we multiply numbers that are 1 or smaller than 1, the result, the product, will be smaller, right? So in that case, we can have a decreasing order of these probabilities. So by this little trick, we can basically guarantee that we have rank consistency, that these numbers are in decreasing order from, let's say, a maximum 1 to 0, essentially. And yeah, this is the main idea behind this Korn method. And we have now these two methods, Coral with this weight sharing constraint and Korn with this conditional probability approach, which is a bit more flexible. And in a nutshell, how do these methods compare? Which one should you use, or which one is better? It depends a little bit. So just, again, how these methods work in a nutshell. Coral is based on this weight sharing constraint in the output layer. Korn on this chain rule for probabilities. And doing like a lot of benchmarks and experiments on various data sets, I would say both methods have their place. So for Coral, I mean, it's very easy to implement. And we also noticed that it has a reduced degree of overfitting. And that's probably because the weight sharing constraint acts as like a regularizer. It makes like, it regularizes, let's say, the output layer so that you get less overfitting because the network has a smaller capacity. So in that sense, it's actually not a bad method if you have a small data set. And yeah, it's a little bit more, I would say, robust to overfitting. And it's also relatively fast. For Korn, it's also very easy to implement. I will show you in a few moments. And you have like this higher capacity, and you can model more complicated functions. So in that way, it's a network with a higher capacity, which is nice for certain things. But again, it can also, let's say, more easily overfit. But yeah, both methods perform well. Overall, I would say Korn is a little bit better. It has a slightly better predictive performance overall if you look across different data sets. But yeah, it's a short talk. So skipping over the mathematical details here, how do we actually use that in practice? Because I think that's what matters the most, that we can get something useful out of this. So I wanted to briefly show you how we can, let's say, convert a regular classifier into an ordinal regression model with Korn, just changing 3 lines of code. And yeah, because it's a short talk, there are more examples on this website here for tabular data, text data, image data, and so forth. I have many examples. Here, it's more like the big picture of how you would convert a model into a Korn model. So using Pytorch code as, let's say, a reference because it's easy to read. So assume you have an arbitrary neural network. So some number of hidden layers, could be a convolution network, recurrent neural network, transformer, multi-layer perceptron, whatever you like. So any type of network, it would be compatible with that. And what you do is in the output layer, you just update the number of classes. So you have the number of classes minus 1 here. And that is because the last node would be redundant, like we said before. If we have, let's say, a rating of 5 and we answer rating is greater than 4 with yes, it would imply 5. So we don't need that last node. It's kind of redundant. So the only modification here is we set the number of nodes to number of classes minus 1. So we add this minus 1 here, as I just explained. So that would be change number 1, just reducing the size of the output layer. Change number 2 would be replacing the standard cross-entropy loss. So when you're training a classifier, you usually have a cross-entropy loss. That's usually the standard approach. You just replace that with a Korn loss. So for that, okay, I'm a little bit cheating here because there's a line break. So it's kind of like 2 lines of code and an import from a library here. So, but in a sense, it's one little change that you have to make, changing the cross-entropy with this Korn loss, essentially. So that's change number 2. And then the last change is how you obtain the class labels. So previously, we briefly discussed how we sum up the yeses. So that's all we need to do now. So here, usually when we have a classifier, we take the argmax. So we look at what is the largest value at the output node, and the index of that is the class label. So that would be a regular classifier. For this Korn loss, we change that to a function that I implemented is just summing up the number of yeses, essentially. So there are 3 little changes, and then you get out of a classifier ordinal regression model. And we are not reinventing the wheel. We don't need a new neural network architecture. You can really bring any network you like and make these little changes and have an ordinal regression method. And yeah, if you're interested in using that or seeing an example, I have this GitHub repository where I have hopefully uploaded the slides by now. And if I didn't forget, otherwise, please ping me. And also a few code examples and links to more references. And I also have prepared a short training run, but of course, I mean, live demos go always wrong, at least if I do them. So I pre-recorded this. So here's just a little script in this GitHub repository that you can run, for example. And this would be training a model with Cornus. So it will probably take a while. So it's, I think, 40 epochs. Actually, I put it also in here so I could take a short break, drink a little bit of water, and yeah. But yeah, skipping ahead because we only have, I see, 3 minutes left. So here I'm also using Pytorch Lightning, which is a wrapper around Pytorch because it gives me a few little things that are really nice out of the box. So for example, mixed precision training, it will also automatically train on the GPU. And one thing I really like, it's like something I coded up by hand usually, is like selecting the best model from the multiple epochs. If I train here for 40 epochs, for example, I look at the validation set performance, and here, instead of accuracy, we are using something called mean absolute error. So the lower, the better. So it's the mean absolute error in terms of the predicted label and the actual label, the average or the mean absolute differences across the data set. And then I'm basically selecting the best model based on the validation set, and then I can, let's say, evaluate it on a test set, and then, let's say, use it in practice. Also, yesterday I built a quick demo with Lightning, so it's just a little demo where you can try it out. It's actually based on one of the benchmark data sets in the New et al. Paper from the CVPR 2016 conference. We compared our method on that data set because it was something people used previously. And it's a very flattering age predictor because I only trained it on the range between 18 and 30. So you are at most 30 years old if you use that. I'm a little bit older, but it's a very flattering, let's say, age predictor. It's only a demo just to, if you want to compare how these methods perform on different inputs. Again, the code is here, and also more examples for convolutional networks, recurrent neural networks, and multilayer perceptrons on this tutorial website I put up a few months ago. And with that, I want to thank all the people involved in this project. Wenji Kao, Shintong Shi, and Vahid Miralali, with whom I worked on the various ordinal regression papers. It has been a fun collaboration, and we had a lot of fun over the last couple of years. Lots of coding, lots of long nights implementing all of that and training that and so forth. And also the team from Lightning AI who helped me writing better Pytorch code and Pytorch Lightning code, so I could train that also on multiple GPUs in a distributed setting to speed things up, which was very important for the paper revision because I only had so many weeks for that. Little shameless plug. Also, I have a book that is available if someone is interested in that. And with that, I think we have then maybe a few minutes for questions. So if anyone has any questions, I'm here for 5 more minutes. And of course, for the rest at the conference. So if you have questions afterwards, I'm happy to chat.
Great, let's thank the speaker. Okay, we have some questions here. Aditya asks, have you explored lattice-based methods like TensorFlow lattice to ensure monotonicity in the binary prediction across different ordinal classes?
I have not explored lattice methods. It's maybe something I can add to my ever-growing list, but no, I have not explored those. There is a TensorFlow and Keras implementation of these methods, though. Someone was so kind and was porting that over. If someone wants to compare this to the lattice methods, that would be something interesting, maybe.
Okay, and Yushuan asks, sorry if I missed it, I'm wondering if the ordered logistic regression is different from Coral or Corn.
That's it was maybe a little bit confusing. The question whether it's the ordinal regression is different from Corn and Coral. So there was this. If I go back, maybe a little bit confusing. I skipped over this, but the reference method here in the lower left corner. They didn't give the method a name, so let's say it's just ordinal regression for deep neural networks. And Corn and Coral are different methods for ordinal regression for neural networks. So this one is the one without rank consistency, and Corn and Coral are essentially, you can think of it as modifications of the ordinal regression methods for deep learning, where we fix this rank inconsistency issue. So it's essentially relatively similar, but we have like this guarantee for rank consistency, which we found improves the performance of this method.
Oh. Andres asks, is there a significant impact in terms of complexity, throughput between plain ordinal regression, Coral and Corn?
Complexity, probably in terms of the number of parameters. Actually, Coral is simpler because you don't have, so you have this weight sharing constraint, and because of this weight sharing constraint, the weights in this output layer are all the same, so you have actually fewer parameters than in the regular ordinal regression method. For Coral, I think you should have the identical number of parameters. The only difference is really the loss function and these conditional training subsets that we have. So the Corn function has the same, let's say, complexity in terms of the number of parameters, and Coral has slightly fewer parameters, depending on how big the output layer is, because you have like this weight sharing constraint.
And Ed asks, does Corn's chain rule for probabilities introduce a constraint to compute probabilities sequentially as opposed to in parallel? If so, does this have a performance impact on speed?
That's a very good question. It was something we also discussed yesterday night at the beer garden. It's like, it's a good question, like a general question. So I did the naive implementation with a for loop over these conditional training sets. And yeah, this is not parallelized. This is a little bit slow. However, you could parallelize that, I think, to some extent and write a custom CUDA kernel. But yeah, what we discussed yesterday, that would be beyond my capabilities. So I can't write custom CUDA kernels. That's a little bit beyond, let's say, my comfort zone. But yeah, I think you could certainly speed that up. For that reason, Corn might be slightly slower than another, let's say, than Coral, because you have this little for loop. But to be honest, it's not really noticeable. It's like maybe if you train something for 2 hours, it will be 5 minutes longer or something like that. I don't think it's like a big stopper or something.
And Gabriel said, thanks for the great presentation. Did you check the performance of your methods in comparison to standard ordered logit or other ML methods like ordered forest?
We did not compare those to these methods because we focused on deep neural networks here, essentially. The tricky part was also, making sure that we have the same backbone to make it fair. So in that sense, here we use the ResNet 34 backbone. If I would change that to VGG 16 or bigger ResNet, depending on the data set, I would also get better performance. So the forest method would, for example, be more like for tabular data. We also explored tabular data in this data set, in the benchmark. But yeah, we didn't do a, let's say, comparison to classic methods because we thought it's like a little bit unfair if you have, let's say, a different backbone. So that was something to make sure that we are fair and compare everything with the same backbone. The paper, the original paper, here on the lower left, the one that I referenced, the original paper, it used a convolutional network that was slightly smaller than, let's say, ResNet, and the performance was way worse. So we really wanted to make sure we make fair comparisons by using the same architecture here, ResNet 34. But again, it's arbitrary. It's just, I feel like, you could maybe compare it to a forest method or the other methods, the classical statistics methods on tabular data sets. That would be fair. But yeah, we haven't done that. We are only focused here on deep neural networks.
Next question was, what's stopping you from just using normal regression?
Yeah, what is stopping us from normal regression? Nothing, really. You could use it. So also, you could use a regular classifier. Yeah, in this paper, we mentioned they actually compared this to regression and a classifier, and the performance was slightly worse with regression and a regular classifier. Not by much. Your mileage might vary depending on the data set. But yeah, it's a slightly improved performance if you use ordinal regression methods for ordered labels compared to regression. But you could, of course, also use a regression method or a classifier.
So I'm going to mention we actually don't have a talk after this. Am I correct? There's not a speaker afterwards? Okay. So if you're happy to keep going with some questions, we've got a few more minutes. I'd like to give people a chance to take off if you need to. Yes? Oh, you had a question? Let me get to the ones on the list here, okay? Noah asked, have you explored anything with taxonomy-based relationships within your labels, like relationships between 1.1.1, 1.1.2, 1.2.1?
The taxonomy. No, I think it sounds a bit like a hierarchical approach. Actually, no, we have not explored this, but it's an interesting question because this was essentially the motivation behind developing these methods. I was a long time ago, 2017 or 18, I attended a seminar where people used a classifier and a hierarchical approach for, it was a biometric problem, and yeah, here, this was an alternative method that we applied and we found works better. But since 2017, besides the seminar, we didn't really compare to hierarchical methods or taxonomy-based methods.
Felipe asks, what is the reason to treat ranked labels as a binary classification problem versus minimizing cross-entropy rather than, via minimizing cross-entropy, rather than using plain regression, like L1, L2 cost functions?
Honestly, by the way, it feels like it's my PhD defense here all over again. Lots of good questions. Yeah, so I think it's similar to the previous question, why don't we use a regular regression or let's say squared error loss? I mean, we can use that. It's just on certain data sets you will find it won't perform as well. I mean, if you think about this age prediction problem, which was one of the benchmark data sets, you can think of age prediction as like a non-stationary process where if you think of people, let's say the age difference between, let's say 8 and 10 years, it's 2 years, but let's say kids change a lot in these 2 years. And if you think about a person, let's say from 70 to 72, the change might be more like, let's say, I don't know, in terms of the skin texture or something. So in this case, it's hard to compare these 2 years from 10 to 12 to 70 to 72. And in this case, a regular regression would think it's the same distance, which is actually not true. I mean, you can do it. It will work very well. However, we found with ordinal regression, where you don't make this distance assumption, you can get slightly better performance, essentially. So, I mean, it's not impossible, it's just not ideal. And the same is true for classification. We have the classifier here also as reference in the benchmark data sets, and yeah, it performs slightly worse. It's not like worlds different. I mean, it's like, I don't know, an MAE of 3 compared to 2.5. It's slightly worse, but it's, let's say, not the end of the world. So it's still possible. It's just like if you want to get slightly better performance without investing much effort, these 3 lines of changes of code will give you slightly better performance, essentially.
Hey, okay, so let's say an example where the relationship, like the labels have a hierarchical relationship between them. So in those cases, have you, like, can we use non-Euclidean manifolds like Poincare or hyperbolic for the scenarios where you can capture hierarchical relationships between the labels?
I've not thought about it or considered this. The thing is, I think it might be interesting because also specifically with the conditional probabilities, you can do very interesting things. However, it would be very unique to each data set. It would be hard to, let's say, implement a general purpose method because you would have to know about this hierarchy and define it. But I think with these conditional probabilities, you can do cool things where you can apply the chain rule for these, let's say, nodes in your taxonomy or hierarchy. I think that's a very interesting idea. So you don't even have to have, let's say, a full ordinal problem. You can have these subordinal problems. I think that's a cool idea. It's just, I think it's definitely possible, but it would need some tinkering specifically to the data set. Yeah. Thank you.
Everybody's had a chance to ask one question here and ask the other questions. You're welcome to talk to the speaker afterwards, I presume. So let's thank our speaker again. And that's it for this session. Thank you.
Yeah, thank you everyone for attending. It was fun.